Good day, everyone, especially to Professor Lausa. I am Remedio John Gabriel, and just call me Gab for short. For this day's topic, I will be giving you additional problems in calculating Coulomb's law that are a bit complicated. But before that, let me also present to you a recap of the steps in solving Coulomb's law problems. So enough time for dilly-dally, and let's start my discussion. Currently presented on the screen are the steps that we should remember on solving Coulomb's law problems. First, we must identify and list all the known information in variable form. Second, list the unknown or desired information in variable form. Third is to convert the units of every variables if necessary. Because what if the problem only gives you microcoulombs instead of coulombs? So of course, if you want to convert microcoulombs into coulombs, then we must remember that microcoulombs into coulombs is equal to times 10 to the power of negative 6. So that's it for the third step. Fourth is to substitute known values into Coulomb's law equation and use proper algebraic steps to solve for the unknown information. In some cases and for some students, it might be easier to first do the algebra using the variables and then perform the substitution as the last step. Fifth is to apply PEMDAS, of course. We need to use PEMDAS in solving our problems because if we don't use PEMDAS, then we would complicate things. Sixth is to cancel the units that are very unnecessary. Of course, it will be redundant if we will be going to use the units that are unnecessary, and that will, of course, complicate things. Seventh, if variables exceed the hundreds place value, immediately round off to the nearest hundreds place. Of course, we need to do that all the time. 8. Round off your answer or answers to the nearest hundreds. Of course, we always need to do that. And lastly, do remember the values of the corresponding measurements. So, once again, we will be recapping this. So, for millicoulombs, it is equal to times 10 to the power of negative 3 in coulombs. Then, for the microcoulombs, it is equal to times 10 to the power of negative 6 in coulombs. Nanocoulombs is equal to times 10 to the power of negative 9 in coulombs. And lastly, for the picocoulombs, it is equal to times 10 to the power of negative 12 in coulombs. So yes. Now let's proceed to those 4 problems that I am preparing for the discussion. The first problem for example B. 2 balloons are charged with an identical quantity and type of charge, which is negative 6.25 nanocoulombs. They are held apart at the separation distance of 61.7 centimeters. Now, determine the magnitude of the electrical force of repulsion between them. Of course, in this problem, it is said that there are 2 identical negative charges, which all means to say that the balloons possess repulsive force. Now, anyways, let's proceed to the given variables. Under the given in GAPSA, or the given as formula, solution, and answer, our initial and final quantity of charge has a value of negative 6.25 nanocoulombs, which is converted into coulombs, and that will be equal to negative 6.25 times 10 to the power of negative 9 coulombs. Our separation distance will be equal to 61.7 centimeters, which is then converted into meters, and thus it is equal to 0.617 meters. 0.617 meters, yes. And for the electrostatic force, which is the missing value, we need to find it. Okay, so the formula to be utilized in this problem would be the force or I mean the force the electrostatic force, which is equal to the Coulomb's law constant times the first quantity of charge, which is the initial quantity of charge, times the final quantity of charge divided by the squared of the separation distance. Now let's proceed. Now let's find out how it is solved properly step by step. For the solution, we need to input our formula, then plug in our variables. The K, which means the Coulomb's law constant, is equal to 9.0 times 10 to the power of 9 newtons times to the quantity of meter squared over Coulomb squared. Now let us put this into mind that the technique of PEMDAS is really crucial for this problem to be solved. Now, let's first multiply the quantity of 0.617 meters and squared. Quantity squared. Okay. Then we get the value of by multiplying 0.617 meters by itself, we will get the value of 0.380,689 meters squared for the squared value of the separation distance. Next, multiply the two identical quantities of charge, both the initial and the final quantities of charge. So, if we multiply negative 6.25 times 10 to the power of negative 9 coulombs by itself, then we will get 3.90,625 times 10 to the power of negative 17 coulombs squared. So that's for multiplying both final and the initial quantities of charge. Now let's all remember to cancel out units. The unit of Newton will be the only unit remaining from the Coulomb's law constant. Now, for the final act, divide 3.90,625 times 10 to the power of negative 17 to 0.380,689, and you'll get 1.0261004 times 10 to the power of negative 16. Now multiply this by the Coulomb's constant, which is, or the remaining of the Coulomb constant, which is the 9.0 times 10 to the power of negative 9 newtons without the meter squared over the Coulomb squared, so without those. Then you'll get 9.2,349,004 times 10 to the power of negative 7 newtons. Then round off this to the nearest hundreds. Then you get the final answer, which is 9.23 times 10 to the power of negative 7 newtons. My god, that was exhausting. So anyways, that's for the first problem. Now let's proceed to the second problem in example B. Okay. Two balloons are charged with an identical quantity and type of charge, which is the negative 5 meter coulomb, microcoulombs. They are held apart at a separation distance of positive 3.0 centimeters. Oh my god. Determine the magnitude of the electrical force of the electrostatic force of repulsion between them. Okay. The same from the first problem, it is said that there are two identical negative charges, which all means to say that the balloons possess, again, repulsive force. So, now let's proceed to the GAPSA thing. Now, under the given in GAPSA, our initial and final quantity of charge have the value of, both have the value of negative 5.0 microcoulombs, which is converted into coulombs, and that would be equal to negative 5 times 10 to the power of negative 6 coulombs. Now, let's proceed to the separation distance. So, our separation distance will be 3.0 centimeters, which is converted into meters, and thus it is equal to 0.03 meters. Oh my god. Electrostatic force is missing, and thus we need to find the electrostatic force, just like the other problem or the last problem. Okay, so the formula to be utilized in this problem would be the same, which is the electrostatic force which is equal to the Coulomb's law constant times the initial quantity of charge times the final quantity of charge divided by the square root of the separation distance. Now, for the solution, we need to input our formula. Then plug in our variables, of course. We need to plug in our variables after distinguishing the formula. Okay. Again, use PEMDAS because it is very crucial. Okay. Now, let's first multiply the quantity of 0.03 meters squared. Then, we will get a value of 0.309 meters squared for the squared value of the separation distance. Next, multiply the two identical quantities of charges, both initial and final quantities of charges, so that we would get 2.5 times 10 to the power of negative 11 coulombs squared. Okay. Now my saliva is dried out. Okay. Now let's proceed. Again, let's all remember to cancel out the units. Of course, we need to cancel out the units. So, the unit of Newton will always be the remaining unit from the Coulomb's law constant. Now, for the final act, again, divide 2.5 times 10 to the power of negative 11 to 0.309, and you'll get 2.7777777 or 2.77s and 8 times 10 to the power of negative 8. Now multiply this by the Coulomb's constant, which is the 9.0 times 10 to the power of negative 9 newtons, without the meter squared over Coulomb squared, of course, without those two. Then you'll get, of course, 250 newtons, and this would be our final answer for our electrostatic force, which is again equal to 250 newtons. Now that's for the second problem. Now let's proceed to the third problem, which is the first problem in example C. Oh my god, I want to drink water, but I don't have water with me. Okay. Now, let's just proceed. So, for the first problem in example C. Two balloons with charges of positive 3.37 microcoulombs and negative 8.21 microcoulombs attracted to each other with the force of 0.0626 newtons. Okay. My god. Napakamot ako. Now, determine the separation distance between the two balloons. Now, In this problem, as you can see, it is stated here that there are different types of charges being present. One is negative and the other one is positive, and thus we could conclude that there is an attractive force that is being observed in this problem. Okay, now let's proceed to the GAPSA. Now, under the given in the GAPSA, the quantity or the first quantity or the initial quantity of charge is equal to the positive 3.37 microcoulombs, which is then converted into coulombs. As always, it should be converted into coulombs. Thus, it is equal to, it will be equal to, oh my god, napakamot na naman ako. It will be equal to positive 3.37 times 10 to the power of negative 6 coulombs. Then, for the second quantity or the final quantity of charge, which is equal to negative 8.21 microcoulombs, which is converted into coulombs. Of course, it should be converted into coulombs. And thus, it will be equal to negative 8.21 times 10 to the power of negative 6 coulombs. That is for the second quantity. Next, for the electrostatic force, we need to use the negative force value since the two identically charged quantities attracts to one another, of course. Thus, we will have negative 0.0626 newtons as our electrostatic force. Okay. The separation distance is what we should find. So yes, that's for the acid. For the utilized formula, of course, we need to utilize some formulas for that. We need to first get the derivative of the separation distance because yes, we only have the Coulomb's law equation, but we need to use or we need to find the separation distance. Of course, we need to find the derivative of the separation distance. So first, for us to find the derivative of the separation distance, we will first use the Coulomb's law equation. Then, we need to transpose d squared to the left side of the equation. Next, we need to transpose the FLE or the electrostatic force to the right side of the equation. Then we both get the square root of the left side and the right side. So square root the left side and the right side. Okay. Then you'll get the derivative equation of the separation distance, which is equal to d, or the separation distance is equal to the square root of the quantity of, oh my god, the quantity of the Coulomb's law constant times the quantity or the initial quantity of charge, which is equal to times the quantity of the second quantity or the final charge. The final charge divided by the force elect or the electrostatic force. For the solution, we need to use the derivative equation of the separation distance. So after that, we need to input all the variables. Yes, the variables, the values. Okay. Then always use PEMDAS as always. Again, I am going to be redundant by this, but yes, use PEMDAS always. Okay. Then multiply the initial and the final quantity of charge. So 3.37 times 10 to the power of negative 6 coulombs times negative 8.21 times 10 to the power of negative 6 coulombs will then be equal to negative 2.76677 times 10 to the power of negative 11 coulombs squared. Okay, it's squared. Okay. Next, cancel out the units. the Newton, and the Coulomb squared. Okay, multiply the Coulomb's law constant to negative 2.76677 times 10 to the power of negative 11 Coulomb squared, and you'll get negative 0.2490093 meters squared. Then divide it by, of course, you need to divide it by the newtons, which is negative 0.0626. Now you'll get the square root of 3.977784345 meter squared. Of course, if you will get the square root, you must first round it off to the nearest nearest hundredths place. Oh my god, why did I but I just said negative. Okay, so yes, round off to the nearest hundreds, then you'll get the square root of 3.98 meters squared, which is equal to positive 1.994993734, or you should round it off to the nearest hundreds, and it will be equal to our final answer for the separation distance, which is equal to none other than positive 1.91 meters for the separation distance. That is our final answer for this problem. Now, let's proceed to the final problem for today's discussion. Oh my god, it is exhausting. Okay. Now, let's proceed to our last problem, which is the second problem for example C. Two balloons with charges of positive 1.0 microcoulomb and the second, which is negative 5.0 microcoulomb, attract to each other with a force of 50 newtons. Now, determine the separation distance between the two balloons. Now, the same from the last problem, it is stated that there are different types of charges being present. That is why we would conclude that this problem also has an attractive force that is being observed. Okay. Under the given in GAPSA, okay, always. So, quantity 1, or the initial quantity of charge, is equal to positive 1.0 microcoulomb, which is converted into coulombs again. Of course, again, we need to convert it into coulombs. Thus, it is equal to 1.0 times 10 to the power of negative 6 coulombs. And for the final quantity of charge, it is equals to negative 0.5 microcoulombs, which is converted into coulombs, and thus it is equal to negative 5.0 times 10 to the power of negative 6 coulombs for the electrostatic force. And thus, we need to use negative force value since the two identically charged quantities attracts to one another, and thus we need to use negative 50 newtons as for that one. Okay. Now, for the separation distance, that is what we need to find. Okay. For the utilized formula, we need to use the derivative equation for the separation distance. Okay. That we are using earlier. Okay, not later. Okay. For the solution, use the derivative equation of the separation distance, and then input all the variables. Of course, always input all the variables before you solve. Then use PEMDAS as always. Then multiply the initial and the final quantity of charge. So, if you multiply 1.0 0 times 10 to the power of negative 6 to 5.0 times 10 to the power negative 5.0 times 10 to the power of negative 6 coulombs, all of them are coulombs, then you'll get, so if you multiply 1 times 5, it is of course equal to 5. So you'll get negative 5.0 times 10 to the power of negative 12 coulombs squared. Okay. Next, cancel out units. Of course, you need to cancel out the units, newtons and coulombs, in order to get the... Okay, my God, kumakati yung ulo ko. We need to get the meter squared, or the separation distance. Now, multiply the column's law constant to negative 5.0 times 10 to the power of negative 12, and you'll get negative 0.045 meters squared. Okay, and then divide this by, or divide it by negative 50 newtons, or negative 50 because we canceled newtons, so we need to divide 0.045 meters squared by 50, or negative 50, then you'll get, then you'll get the square root of 9 times 10 to the power of 9 times 10 to the power of negative 4 meters squared. And of course, the square root of this will be your final answer for the separation distance, which is equals to positive 0.03 meters. Okay, now that is for our final problem. Thank you for listening to my discussion, and I know it's been exhausting listening to me, but yes, I do hope that you have learned something from the discussion. And before this video will end, I would like to give you all an activity slash an assignment, or an assignment which will be given as okay, activity slash quiz, which it will be given as an assignment. Okay, that's the point. Okay, now the deadline of this will be further announced after this video. Once again, thanks for listening, and adios. Peace.